So last time we ended with plotting and adding the trend line and estimated regression equation and the r-squared value on the chart in Excel. So let's go back to Excel, and what we didn't do is we didn't do the correlation coefficient. So remember, the correlation coefficient we use equals CORREL. And notice I put a single quote in front of that so that it would not use the actual, it puts it as text. So there's my first array, my x's, my second array, my y's, and we see the correlation coefficient is at 0.93856 that we had seen before. Now remember, reverse it, the correlation coefficient does not matter which order you put stuff in. So if I put the height first and then the stories, it'll give me the exact same correlation coefficient. Obviously, if we're trying to predict one using the other, we should put them in the x and then the y, right? So the relationship is the same regardless of which way we put them on which axis. But if we start to try to do causation or prediction, then we need to make sure we have them in the correct order. The other thing we can do here is we can find the slope of the line using slope, and it wants the y's first, known y, see that little tooltip, and then the x's, and it better come up to be about 9.5, 9.44918, right, which is that one's rounded a little bit. And then to get the intercept, we can just use equal intercept. And again, it wants the y's first, the dependent variable, the thing we're trying to predict, the response variable. And then the x's, the independent variable next, 176.066. Right? So we get the same thing using these equations as we got from there. So now let's go back and talk about what that equation is actually doing. So the model, the linear model, is described by y is equal to beta sub 0 plus beta 1 times x plus epsilon. Beta sub 0 and beta 1 are unknown population parameters. And then the epsilon is the error term. So that takes into account variation around stuff, around the line. So then what we want to do, in order to use this model, we want to estimate the parameters, the unknown population parameters, beta 0 and beta 1, by taking a sample, data, and estimating or calculating values that we think are good representations of beta 0 and beta 1. So to do that, we estimate the intercept and slope. We take the sample, compute the estimated simple linear regression equation as y hat. We put a hat on it saying that it's our prediction, or what we're estimating into the future, or guessing into the future, is equal to b0 plus b sub 1 times x. So the b's are the estimated. We get that from the data. The betas are the unknown population parameters in the model. So then notice that the epsilon term, the error term, dropped out. So what happened to it? Well, to get to this point, what we did is we took the expectation of both sides of the equation. When we do that, the epsilon term drops out because of some assumptions that we make with the error term. In particular, we assume that the error term is normally distributed with a mean of 0 and a constant variance. So go back to your stat course and try to remember what all that stuff means, right? So in essence, its expectation is 0, so it does not show up. So this is the b sub 0 here was the 176 and change that we got from our buildings. The b sub 1 is the slope that we found was about 9.5, 9.44 something, right? And x is our independent variable, in this case, number of stories. Right. So how do we know that? How do we actually estimate B0 and B1? Well, Excel did it for us, right? We did it two ways. We added a trend line and showed the equation on the chart. The other was without having to add a chart, we could do slope and intercept to get those two. And then what it's doing in the background is using what is called ordinary least squares, and it's minimizing the sum of the squares. So to find that best fit line, we use the objective of minimizing y sub I, the actual, so the actual building height, minus what we predicted for that particular building, y hat sub I, square that difference, that deviation, hence square, and then add them all up for all of them. So we had, in our case, remember this big sigma symbol is summation. I equals 1 to n. We had 7 data points, so this would expand into 7 different terms, where each term represents one row of our table. Right? So we do that. And then minimize the sum of those squares. So graphically, what that looks like is the actuals are the dots, and here's the line that we fit, and we take the distance and then square it. So we're adding up the areas of all of these squares, all 7 squares. Don't get hung up. Like this square right here is going the opposite direction and everything else. I did that so that it wouldn't overlap with these other squares over here to make it look too messy. So don't get hung up on that. Instead, just notice that what we're doing is we're finding the areas of these squares, adding them up, and this line that is shown here happens to be the one that minimizes the sum of all of those 7 squares. So that's what we want to do. Right? So how do we do that? How do we know that that line that we put there is in fact the best one? Well, calculus can show us that the best fit line can be found using the following equations for beta b sub 0 and b sub 1. We calculate the slope first. Right? We estimate the slope first. Right? So it's the actual x value minus x bar, which is the mean of x, times the quantity y sub I, the actual, minus y bar, the mean of the y's. Right? Multiply those together, add them all up. Right? That's the numerator. Denominator is the x minus the x bar squared. Add all those up. So again, we'll have 7 terms in the numerator, 7 terms in the denominator, because we have 7 data points. That gets us our slope. We then use the slope b1 over here, where we take the mean of y, subtract out b1 times x bar. Right? So we can do this manually. Right? So that is what we're trying to do. We're trying to minimize those squares. Find a line that minimizes those squares. And we're saying that the one that we found using 2 different ways in Excel is that best fit line.